Okay, so to recap the discussion last time, we considered uh, instantaneous rates of change, right? What's happening at the moment level if something is changing? How can I describe that rate? Okay. We also talked about tangent lines and their slopes, slopes being of particular interest to us. And we talked about this new idea called the derivative. That is at all legible. And it turns out that all three of these things are the same, right? They're all what happens if you take a limit of the change in the outputs of a function divided by the change in the inputs of the function, right? This is an average rate of change, right? How much did the outputs change divided by how much the inputs changed over the same interval, right? And I want to take a limit as that change in the inputs goes to nothing, right? What happens if delta x goes to 0? That's not as legible as it could be, but that's what it says, right? Delta x goes to 0, right? Alternatively, we saw this definition. The limit as h approaches 0 of f of x plus h minus f of x all divided by h. Right? So h is some minuscule change, right? H is shrinking to nothing. And so the top represents the difference between the function now, f of x, and the function just a moment away from f of x. So there's the change in the outputs in the numerator. And the denominator is that change that's happening. How much change is happening in the input, this tiny amount, h. This is called the difference quotient. And we defined this to be f prime of x, the derivative of f at x. It also represents the slope of the tangent line at any given moment. And it also represents, in applied situations, the instantaneous rate of change of the function at that time. Okay? So all three of these things are represented by the derivative, and the notation that we introduced last time was this f prime notation. So f prime represents all three of these ideas. All right. So, couple of questions, maybe. What does it mean for f prime of x to be things, right? So if f prime of x is going to spit out a number at me, right, for any particular x, right? I say f prime of 3 is 4. F prime of 10 is 0.9, right? F prime of 105,000 is 3,000. Right? When x is representing a number, f prime of x is going to be some value, right? And I'd like to know what that means. So what would it mean if I had a really large derivative? All right, so that's definitely going to be one thing, right? The derivative represents the tangent slope. So if the slope is really, really large, then the tangent lines on that curve are going to be very, very steep, right? So large slopes equals steep curve. Okay? So very small slopes, like 1/10 or negative 0.006, right? Those are going to be very not steep curves, right? Small slope equals not steep, right? Relatively flat. So both of those are geometric descriptions, right? So if I know what f of x looks like, if I have a graph of f of x, then I generally might be able to tell what f prime of x looks like based on the shape of that curve, right? If it's really steep, then f prime of x is going to be large. If it's really flat, then f prime of x will be really small. And I'm referring to large and small here in terms of like absolute value, right? Steepness could be really steep and increasing, or it could be really steep and decreasing. Right? So negative a million is still a large slope. What about in context, though? Okay. So if the power of these functions, right, isn't just that like you plug numbers into them and they spit numbers out, and we might be interested in how those numbers are changing. It's that those functions can be used to represent real life things. So if f of x is representing some value that we're interested in, if it's representing the cost of producing a certain number of goods, or where something is at a given time, or the population of deer, or your salary, or the amount of money in your bank account, right? F prime of x is going to tell you something about that application too. What? If the derivative were really large, right, and the function represented how much money was in your bank account, what would that tell you about the money in your bank account?
Putting a lot of money into it very rapidly or taking a lot out very rapidly.
Yeah, it means that the way that it's changing is very fast, right? So I could be taking money out very quickly, or I could be putting money in very quickly, right? It could be climbing at a really big rate or decreasing at a really big rate. Whereas if it were really small, then it'd be like money just kind of trickling in. It's mostly the same, right? The amount of money in my bank account if it has a small derivative. Right? You just leave money in a checking account or a savings account right now, you're not making any money, right? You're making 0.2% per year or something like that. Something horrible. Okay, so the derivative is all about how a function is changing, right? These are rates of change, right? Calculus in general is all about change, right? So if the slope is large, then the function is changing quickly, and if the slope is small, then the function is changing slowly. Pretty good? Okay. Well, what about this? What about whether the function is positive or negative or zero? What about the sign of the derivative? Okay. If f of x represents how much money is in my bank account, would you rather have a positive derivative or a negative derivative or a zero derivative? Why positive? What does a positive derivative tell you about your bank account that you would prefer that instead?
I don't want anything associated with money to be negative.
Fair enough. Right. Well, I mean, you could want things, right? So interest rates, for instance, I might like the derivative for an interest rate to be negative. That would tell me that interest rates were declining. Means that I might be able to refinance my mortgage or something like that and save some money. So if f of x represented my bank account, right, geometrically a positive derivative is a positive slope, right? Because the derivative is the slope. So if the derivative were positive, am I expecting more money, less money, or the same amount of money next month? More money. Right? I'm expecting it to increase. Okay? The slope is positive, it should be getting bigger. And so a negative slope is going to be a decrease, and a zero slope will be what? The same. Yeah. It'll just be, right? It'll be flat. Zero slope, it'll be just as high now as it will be then. Right. So positive slope slash derivative, that means that we are increasing. Right? And the bigger that number is, the faster it's increasing. Negative slope or derivative is going to mean decreasing. And again, the larger that number, the faster it will be shrinking. And a zero slope or derivative means that it's constant. No change. Questions here about what the derivative is telling us?
The slope of 0 equals 1, right? I go with the slope of 0 equals 1.
The slope, if the slope were 0, the slope would just be 0. It doesn't mean that the function is 0. It just means that the function is the same, or it's going to kind of be the same for a moment. Right? It could always be 0. So say, for instance, if a function were just not changing, right? If I had a checking account that didn't give me any interest, right? If my checking account weren't growing at all, and I stuck $200 in, then January my account is $200, and February my account is $200, and March my account is $200. Right? It's not changing, so the derivative would be 0 all the time.
Okay.
But it could be that it's increasing, and then it's going to kind of like pause, and then decrease. So it'll be just 0 for a moment or something like that, or a period of time. It's worth noting that just because we know the derivative, that doesn't tell us any information about what the function is. It just tells us how it's changing. Right? So if the function is representing my bank account and I tell you that the derivative is 0, that doesn't tell you that I have whatever amount of money in my bank account, right? You wouldn't know how much money was in my bank account. You would just know that it's not changing. So that's an important point. All right. Let's think about a couple of specific types of examples. So how about this? s of t is the position of an object that moves along a straight line at time t, then what, I said f prime here. This should be s prime. I'm talking about s. What does s prime represent? So s of t is the position at a specific time. So what might s prime of t represent?
Speed.
Yeah, how fast it's going, right? So it's going to tell, so position is changing, right? Position is s. So the change in the outputs is a change in position. And the input is time. So the change in inputs is a change in time. So the derivative here is going to represent an instantaneous rate of change in position with respect to time, right? So rate of change in position with respect to time. It's a speed. More accurately, we call it a velocity. V-E-L-O-C-I-T-Y. The difference between a speed and a velocity is that a speed is just a size. I'm going 60 miles per hour, 50 miles per hour, 25 miles per hour, and it's driving you crazy. Right? Whereas a velocity has speed and direction. So it's got size and some way that it's going. So if we were in a straight line, there might be a positive direction and a negative direction. Right? I think about going right as being in the positive direction and going left as the negative direction. So I might have a derivative being negative. I've lost position. The net change in position would be negative. So that's going to be moving to the left. Right? So because a derivative might be negative, it's going to have a swing, right? There's a kind of a positive way and a negative way. So we say velocity. You typically don't say things like, oh, I was driving negative 20 miles per hour. Right? Questions about this? My handwriting seems to be getting worse. If S of t was measured in meters and t was measured in seconds, what would the units for S prime of t be? Yeah, meters per second. It'd be meters over seconds. Remember that this is remember that S prime of t is like this limit, right? It's a limit as t approaches 0, or h approaches 0. Let's use the proper thing, right? Of S of t plus h minus S of t divided by h, right? Where this top is a change in S, and the bottom is a change in t. Okay? So this change in S is how many meters S is changing, because S is all about meters. Right? So meters, and the change in t is seconds, because t is measured in seconds. So m over s, right? So meters per second would be the units there. Any questions about this type of scenario?